Okay, today's talk is about Unicity ID. It's about how to use names instead of public keys in Unicity transactions. And I'm starting with motivation and goal of this particular work. And then we will go through some preliminaries about cryptography and about Unicity. And then I explain the mechanisms, how to use so-called name tags or name tokens in the Unicity to achieve the goals. And finally, I introduce a special predicate. We are still in the predicate framework, so everything we will do is in the framework of predicates. So we will introduce a special predicate for such transactions. Okay, so let's start with the motivation. Say we have a certain kind of communication platform. It might be WhatsApp, for example, where people have local names. Say we have Alice and Bob, and in parallel, Alice and Bob might be in the Unicity community. So they have, say, public keys with which they send tokens to each other. But our wish is to send tokens using only the chat without knowing each other's public keys. So public keys are kind of cryptographic material which is which are not human memorizable, and they are inconvenient to use. So why not use names instead? So what we really want to do is to introduce some kind of transactions in Unicity infrastructure that send tokens to names instead of public keys. So Alice sends her token, say it's token A, to Bob using just the name. So how? The point is that after such a transaction, the token is in some kind of a state, and the next transaction to be done needs some cryptographic authentication. So it's not just the next guy who makes the transaction should only know the name. So there should be cryptographic authentication, and that's why in Unicity there are so-called name tags or name tokens that bind names to public keys. So Bob has some kind of a token which claims the binding between Bob's name and Bob's public key. And this everything might just happen like in this conversation box. So Alice just asks Bob whether he has Unicity ID. Bob just says yes, and Alice sends a token to Bob. So what is the motivation of the current work? So the name tag mechanism currently implemented lacks several useful features of public key infrastructure. So public key infrastructure is about binding names to public keys. We don't have revocation, so the name key bindings are eternal and cannot be revoked. But revocation might be necessary in case of private key exposure or loss. There is no expiry. Public key certificates usually have expiry dates to manage risks of unknown key exposure. Just this certificate should be renewed in time to prevent some security breach. And there is no update. So as I said, the name key bindings are eternal. You can't bind another public key to the same name currently. So the goal of this work is to with as small as possible changes to the Unicity infrastructure to enable all of those features. Okay, some preliminaries which you probably know, but I will just go quickly through it. So we have signature schemes with 3 algorithms: key generation algorithm that just generates public key and private key or secret key. There is a signing algorithm that creates a digital signature on a message or message hash M using the private key. And there is a verification algorithm that verifies the signature. And of course, if you create a signature using the signing algorithm, this should verify correctly. And there are some security features that you should not be able to forge other signatures by knowing just the public key. We also use commitment schemes, but it's currently they are not implemented. It's because of security proofs going through. And currently we just use trivial commitment schemes that basically the commitment of any string is the string itself. Okay, so about Unicity tokens. Tokens have state. So the current state is a pair of a owner predicate new and a hash. Hash represents the state, kind of. Any transaction in Unicity has 2 components: the state hash and the contents of the transaction, which should have the new owner predicate, new prime, some random value, and some auxiliary information. To sign a transaction, we have to. The signer has to provide the unlock string U that satisfies the predicate. Again, every predicate also uses the so-called system time, which we will describe later. And also, transactions should be certified by using the Unicity service. Query is sent to the service, and inclusion proof is given back by the service. And for every transaction, we create the so-called certified transaction that contains, in addition to the transaction itself, it contains the unlock string or the signature and the inclusion proof pi. And after such transaction, the state of the token is changed. So the new owner predicate is now the first component of the state, and the hash is just updated based on the random value X in the transaction. Okay, so yeah, so the Unicity service, just recall what it is. It maintains a database or dictionary R. So every value of the dictionary at every key is either empty or it has a value, which is a hash value. And if request is received by the Unicity service, say the the key is the place where which will be occupied after the request. Then it just writes something to the at the place of the key, which depends on the transaction. And you can also ask status queries. You enter, you send the location K, and you will see whether it's empty or not, or what is stored at the key. And we have a verification function that enables to, based on the inclusion proof, it enables to verify which value is at which location. Okay, we want to do everything in the predicate framework. So just quick recall what the predicates are. Every predicate has name, has some parameters, and if we satisfy the predicate, we have to input some values. So system time is one value, transaction hash is the other value, and there is also the unlock string, which we have to enter as the third argument of the predicate. The system time is just a non-negative integer held by the Unicity service, and it's incremented when the contents of the register is certified by the consensus layer of the Unicity. So it's always increasing, and it's incremented at every certification event. Some just examples. So the most basic predicate is the signature predicate, which is basically verifying the signature using the public key as the parameter. Okay, so every token has the first transaction or the minting transaction. So every token is created using the minting transaction. Minting transaction has its own syntax and own semantics, and it depends on the minting policy, which Unicity infrastructure doesn't specify. So there is, for every user domain, there is a certain identifier. We call it domain identifier. It's also called mint suffix in the current implementation. We have minting public key, which is supposed to be known all users of the domain, and there is a minting private key, which depends on the policy, whether it's owned, say, extreme cases, whether if it's owned by just a single entity, or it also the other side of the extreme cases when it's public. Everybody knows the minting key. It all depends on the policy of the domain. Mint transactions are somewhat special in Unicity, and their validity depends on the particular user domain. The minting transaction, certified mint transaction, is a triple, where D0 is a transaction, and D, the data part, should contain the first owner's public key, token identifier, and auxiliary information, auxiliary data. And there is a subfield in the auxiliary data, which is the mint purpose. It just indicates what is the token about. For example, the token might be name token, and in this case, this P indicates that the token is a name token. And there are some conditions that should be satisfied. Signature should verify with sigma 0 should verify with the minting public key, and a location in the Unicity service that is the hash of the minting public key, and H0, which is the first state hash, so to say, and it's computed from the token identifier and the domain identifier. So this specifies how mint transactions should look like in Unicity. Okay, so name tokens. Name tokens are the mechanism how to create Unicity ID, and name token is a special type of Unicity token that binds a name to a public key, and it's equivalent to a public key certificate. And name tokens are just minted, and there are no further transactions with them, although technically it would be possible. We will use this feature later. Note that we try not to introduce any big changes in the current implementation of the Unicity code. So okay, and for name tokens, the Unicity the token identifier is computed in a special way. It's a deterministic function of the name when we use a kind of fixed constant and hash it together with the name. Yeah, so if you have a minting transaction, the public key field, the PK0, means the certified public key. So this way it binds the name and the public key. And the purpose field should indicate that this is indeed a name token. And we can easily prove that if H is collision resistant and if the Unicity service behaves in a specified way, then it is not feasible or not possible practically to create bindings when we have two different public keys to the same name. So it's not practically possible, or we can say practically impossible to do that. Okay, so name tags, actually using name tags is equivalent of using certain kind of predicate. So we try to express everything, as I said, in terms of predicate. So sending token to a name, it actually means that that the next owner predicate is the so-called name tag predicate, which has 3 parameters: the domain-specific constants and the name. And to satisfy the predicate, the signer has to provide unlock string with a signature and a triple where PK0 is the public key, some auxiliary information, and an inclusion proof by 0. And this predicate is defined as follows. It's the predicates always have standard arguments: the system time, message hash, and the unlock string. And it's true if D0 is in this form, H0, if we defined H0 this way, then the purpose of the transaction, of the purpose field of the auxiliary string should be name token. So the purpose is a name token. Signature should verify with the public key. So this is about the next transaction with the token, when the token is in this state. Signature should verify, and the name token should the name token has been certified. So this means that the place, the hash of this is the storage key. So this key should be occupied in the repository of Unicity service. So this function f inclusion means that it should be evaluated differently by users and by Unicity service. Unicity service just checks whether we stored at this key. It doesn't look at the proof at all. At user level, it has to use the verification function, and we can prove that this will not make any confusions. So as far it is used in ordinary way as we use it in the Unicity infrastructure. So no confusion will arise. Okay, so first we will gradually introduce the new properties that we wanted to achieve. So first, revocation. Revocation itself alone, it makes not much sense, because if you just are able to revoke your name key binding in the current setting, you can't renew it. You can just you can just revoke it. But yeah, so okay, so suppose we have a name tag which is created by a certified mint transaction. Those identities should hold in this case, and after such transaction, the token is in the state big K0 and H0, which is computed like that. Though in the current setting, there are not supposed to be any further transactions with the name tokens, but just imagine that someone does a next transaction with the name token. Say the next transaction is T prime. And if this transaction is certified, it blocks the state, the current state, after which we can see from the repository that this location, this key is not empty anymore. So this can be used like a sign of revocation. So if there are no transaction, there have been no transactions with the name token, we can say that it is valid, it is not revoked. But if the next transaction was made, then we can say that the token is revoked. So this can be expressed in a new predicate that includes this possibility. It has the parameters of the predicate are the same as in the original name tag predicate, but the unlock string includes revocation, non-revocation proof, which is non-inclusion proof. So this proof is basically to show that next transaction with name token has not been done. And yeah, so this just introduces a new line to a new condition, which just certifies that the state the name token was after its minting hasn't been spent. And this proof should be taken either at the same time when the signature was formed, the next transaction with the token, not with the name token, but when a token is in such a state, then the next transaction should show it. Show the non-spent condition after the signature itself was created. So this is non-revocation check. And it uses a special function again, which should be evaluated differently by the Unicity service and by users. Unicity service just defines this function to be the system time, and at the user level, it just extracts the time from non-inclusion proof or inclusion proof. Okay. Now the expiry. Expiry is we can in a similar way add some properties to the required properties to the unlock string, and we assume that in the auxiliary string you may add there a special expiry time field. So this is to_exp, which you define at what time your name token will expire. And it just introduces additional verification condition to the predicate. So this means that either there is no expiry time, this means that the token is not expiring, the name token, or current time is less or equal than the expiry time. So this is called expiry, non-expiry check. Okay, and finally, we want to renew the name key binding. So we want to use the same name and introduce a new public key to the same name. Again, let the minting transaction be T0, and it satisfies the usual condition, and the token is after this transaction is in this state. And imagine that we make a next transaction, regular transaction with data part T1. T1 contains, as usual, a public key, say it's PK1, a random string and auxiliary string, and we can kind of interpret this as a new binding of the same name token. So now we have two transactions, and the last transaction defines what is the currently valid public key that corresponds to the same name. Okay. So if one point is that if T1 was the last transaction with the token, then the state after T1 should not be spent, should be unspent, and this can be checked. Okay. Any questions? And we can generalize this. So we can update the public key with many transactions. So with T1, T2, up to Tn, and then we have a sequence of states, the last of which should not be spent. And this is how we recognize that this Tn is indeed the last updating transaction that defines the currently valid public key and name binding. And this, having this in mind, we can construct finally the thing we really wanted is updatable name tag predicate. It has the same parameters, but it has somewhat more complicated unlock string, which also instead of just containing the minting transaction, it also contains information about subsequent updating transactions. We can later think how maybe we can somehow compactify this by defining xi not to be random or constant or something, but in general this is like that. And it just adds some an additional verification line to the verification condition of the predicate. So it's called chain check. You just have to follow the updating chain and to see whether the right keys have been occupied in or spent in the Unicity registry. And note that if this list is empty, then it can be interpreted that n is just 0 and there are no computations here, and there is no check in line 4. And in this case, the predicate is equivalent to the previous predicates. So it's compatible to the previous version of the expired and revocable name tag predicate. Yeah, so yeah, there are some open issues as well. So which we will study first, how to make those the Unicity ID more secure. So we don't have studied particular minting policies, which might be important to prevent someone to occupy others' names or something like that. So there are some open issues to study as well here.